Meganeura. Meganeura was a genus of giant griffinflies, related to dragonflies, that lived about 300 million years ago in the Carboniferous period. Fossil wingspans measured up to 70 centimeters, making them the largest known flying insects. Their bodies were long, slender, and equipped with strong mandibles. Unlike modern dragonflies, griffinflies had no ability to fold their wings, which remained extended at rest. Their large compound eyes and predatory mouth parts suggest they hunted other insects in flight, seizing prey with spiny legs before consuming it. Oxygen levels in the Carboniferous atmosphere were around 30 to 35%, much higher than today's 21%, allowing diffusion-based breathing to support such large body sizes. Arthropleura, though technically a millipede relative and not an insect, deserves mention for its sheer scale. It reached lengths of 2 to 2.5 meters, making it the largest known land invertebrate in Earth's history. Its body was composed of numerous armored segments with paired legs, and trackways show it moved across swamp forests in search of decaying plant matter. While primarily herbivorous, its size alone would have been intimidating to any contemporary animal. Paleodictyoptera. These were an extinct order of insects often called six-winged insects. They lived from the Carboniferous into the Permian, with wingspans up to 55 centimeters. They had 3 pairs of wings, forewings, hind wings, and an additional pair on the thorax. Their long, beak-like mouth parts suggest they fed on plant fluids, piercing stems to extract sap. Fossil evidence indicates they were among the first large insects to dominate terrestrial ecosystems before the rise of more modern groups. Archimylacris. Archimylacris was a genus of large, cockroach-like insects that lived during the Carboniferous and Permian periods. Unlike modern cockroaches, which are flattened and adapted for hiding in crevices, Archimylacris had a more oval, beetle-like body form, with long legs and well-developed wings. Fossil specimens show body lengths of up to 10 centimeters, considerably larger than the average cockroach today. Their wings bore intricate venation patterns, and unlike many modern cockroaches, they were capable of sustained flight. Mouth parts were generalized, allowing them to feed on both decaying matter and plant tissues. They lack the euthyca, or egg case, that modern cockroaches use, indicating their reproduction relied on simpler, direct egg-laying strategies. Their abundance in Carboniferous deposits suggests they were successful generalists in swamp ecosystems. Blatoids. This is the broader group that included Archimylacris, who were early relatives of cockroaches and mantids. They appeared as some of the first insects to evolve chewing mouthparts robust enough to exploit a wide range of foods, from detritus to living vegetation. Some forms exceeded 15 centimeters in length, making them far larger than the vast majority of insects today. These body plans foreshadowed the adaptability of modern cockroaches, which remain among the most resilient insect lineages. Another notable cockroach-like form was Spiloblatina, found in Permian strata. It shared the large size and winged morphology of Archimylacris, but developed further modifications of the thorax and forewings. These features enhanced flight and provided additional protection to the body. Fossils of these insects are common in compression deposits, indicating they were widespread across Permian lowlands. Their persistence until the end of the Permian reflects their adaptability across changing climates. The cockroach-like blatoids were not predators, but their size, mobility, and abundance made them dominant components of Paleozoic insect faunas. Their success demonstrates that insect gigantism was not restricted to predators like griffinflies, but extended to generalist and scavenging forms as well. While modern cockroaches seldom exceed a few centimeters, their Paleozoic relatives reached sizes that would appear monstrous today, filling ecological niches with little competition from vertebrates or more advanced insect groups. Griffinflies. Griffinflies, the group to which Meganeura belonged, were among the first aerial predators. Their large compound eyes provided wide visual fields, while spiny legs allowed them to intercept prey during flight. Fossil evidence from wing venation indicates powerful flight muscles that supported long glides and sudden maneuvers. They hunted other insects in open air, filling a role similar to modern dragonflies, but on a much larger scale. Their dominance declined by the end of the Permian as oxygen levels fell and competition from new insect lineages increased. Scorpionflies. Scorpionflies, belonging to the order Jaekelopterus, first appeared in the Permian and became diverse in the Mesozoic. They had elongated faces ending in downward curved rostra, equipped with biting mouthparts. Males of some fossil species bore enlarged genital segments that curled upward, resembling the stingers of scorpions, which is how they received their common name. Fossils from the Jurassic, such as Jurassipanorpa, show body lengths of 3 to 4 centimeters, while later species developed wings with bold patterns possibly used for display or warning. Scorpionflies were omnivorous, feeding on decaying matter, small arthropods, and nectar, but their appearance was intimidating compared to modern insects of similar size. Mantis. Mantis relatives emerged during the late Paleozoic from cockroach-like ancestors. Fossil genera such as Santan mantis from the early Cretaceous display, the specialized forelegs adapted for seizing prey, a hallmark of mantids today. These forelegs folded against the thorax when not in use, armed with spines to grip struggling prey. Although Cretaceous mantids were not as large as griffinflies, their ambush predation strategy marked a significant evolutionary innovation. They occupied forest understories where their camouflage and rapid strike gave them advantage over other insect predators. Neuropterans. Neuropterans, including ancient lacewing relatives, also produced predatory larvae during the Mesozoic. Some larvae preserved in amber possessed exaggerated jaws for piercing prey. These jaw structures worked as paired tubes, allowing simultaneous injection of digestive fluids and withdrawal of liquefied tissues. Although small compared to Paleozoic giants, these predators demonstrate the refinement of specialized mouthparts as insects diversified. These predatory insects illustrate the shift from sheer size, supported by high atmospheric oxygen in the Carboniferous, to specialized anatomy and behaviors in the Mesozoic. As oxygen levels stabilized, gigantism became unsustainable, but insects continued to occupy apex predator niches through innovations in vision, flight, and feeding mechanisms. Jaekelopterus, a Devonian eurypterid, or sea scorpion that reached lengths of more than 2.5 meters. It was the largest arthropod ever discovered. Its body was divided into a broad head shield, segmented trunk, and a paddle-like tail for propulsion. The front limbs were armed with spines for grasping fish and smaller arthropods. Large compound eyes suggest active predation in shallow seas and rivers. Giant water bugs, Belostomatidae relatives. Fossils from the Mesozoic show water bugs that exceeded 10 centimeters in body length. They hunted from ambush, seizing prey with raptorial forelegs. Their beak-like mouthparts injected digestive saliva into prey, usually fish or amphibians, before drawing out liquefied tissues. Even modern relatives are known for powerful, painful bites. Predaceous diving beetles, Didicidae. Early representatives of this family are found in Mesozoic freshwater deposits. Adults had streamlined bodies with large, oar-like hind legs adapted for swimming. Their larvae, called water tigers, bore curved, hollow jaws. These jaws injected enzymes into prey and siphoned fluids back out, allowing them to consume small fish and aquatic invertebrates. Griffinfly nymphs. Juvenile stages of giant griffinflies such as Meganeura lived underwater. Fossilized labial mouthparts show they possessed an extendable lower lip, or labium, which shot forward to grab prey. Given that adults reached wingspans of up to 70 centimeters, the nymphs would have been correspondingly large, making them dominant freshwater predators of the Carboniferous. Sphecomerma. This genus from Burmese amber, about 99 million years old, represents the earliest known true ants. They combined wasp-like traits with features of modern ants. Body length reached around 5 millimeters, with long legs and elbowed antennae. Their mandibles were large relative to body size and adapted for seizing small prey. Colonies were likely small, but they show the first steps toward eusociality, living in cooperative groups. Cretaceous wasps. Hunting wasps of the Cretaceous period developed stingers derived from ovipositors. Fossils reveal long, sharp stingers capable of delivering venom, used to paralyze prey or defend against threats. Some species grew larger than modern counterparts, exceeding 3 centimeters in length, making them formidable aerial predators among other insects. Cretaceous termites. Early termites appear in Cretaceous amber with clear cast systems. Worker termites were smaller, adapted for processing wood, while soldier casts bore enlarged mandibles or chemical spraying glands. Colonies recycled plant material on a large scale, altering ecosystems and creating the earliest evidence of mound-building behavior. Melitosphex. This fossil insect, also preserved in Cretaceous amber, is the earliest known bee. Measuring only about 3 millimeters, it carried branched body hairs specialized for pollen collection. Its anatomy shows the transition from predatory wasps to pollinators, establishing a mutualistic link with the first flowering plants. Paleodictyoptera, an extinct order of large Paleozoic insects, some with wingspans over 50 centimeters. Their elongated beaks pierced plant stems to extract sap. But what made them notable was the presence of extra wing-like lobes on the thorax. These gave them a strange, six-winged appearance, unlike anything alive today. Their size and abundance made them visually imposing members of early forests. Meganeura mandibles. Griffinflies such as Meganeura possessed oversized mandibles with sharp edges for cutting and consuming prey. Fossils show heavily reinforced mouthparts relative to body size. Combined with spiny legs, these adaptations made them apex aerial predators of the Carboniferous, unmatched among flying insects. Cretaceous scorpionflies. Members of the order, Meganeura, developed elongated faces with downward curving beaks and biting mouthparts. Some males had enlarged tail segments curled upward, resembling scorpion stingers. While these tails were not venomous, the display made them visually threatening. Their fossils indicate omnivorous diets including carrion and soft-bodied prey. Early wasp stingers. Cretaceous wasps show some of the first evidence of stingers capable of delivering venom. These were modified ovipositors, originally for egg-laying, transformed into piercing organs. Fossil specimens with long stingers suggest they could penetrate the exoskeletons of other insects, making them among the earliest venomous predators of their kind. Cycad-feeding beetles. Fossils preserved in Cretaceous amber show beetles specialized to feed on cycads, which contained neurotoxic compounds. Adaptations such as hardened forewings and specialized digestive systems allowed them to tolerate poisonous plant tissues. Their ability to exploit toxic food sources represents one of the earliest insect-plant arms races.